If you would recall, we've been comparing line integrals and flux integrals. I guess better we should say we've been comparing flux integrals to what we did with line integrals. They have a similar structure. We're integrating, in both cases, we're integrating a vector field, but in the case of line integrals, we're integrating a vector field over a one-dimensional curve, and in the case of a flux integral, we're integrating a vector field over a two-dimensional surface, or should I say, through a two-dimensional surface. The pictures that we had for line integrals were to imagine that the vector field is the wind and the curve is the path of a bird flying in the wind. And so our line integral could represent the work done by the bird to fly in the wind, or the work done by the wind to push the bird around. And with flux integrals, we identified the word flux as being the word flow. And so we imagine that the vector field is, say, the flow of air or the flow of water, and S would be like a net through which the water is flowing. If the vector field represents the velocity of the water, then the surface, what we are doing is calculating how much water is flowing through the surface, multiplying that by dA, and so we're calculating the total volume of water that's flowing through the surface. So the speed of the water would be something like centimeters per second, and the area would be, say, square centimeters. So the product of those two quantities would be cubic centimeters per second. How much water is flowing through the surface. To generalize, we just need to look at other applications of the dot product. What could our vector field represent? We have to think about what our vector field could represent and what it could mean with a dot product with a two-dimensional quantity. So anything that we can use with multiplication, anything that we can calculate through multiplication is something that we can calculate through integration. So that's the comparison between line integrals and flux integrals. Then we have to talk about how we actually make these go, because these are generic statements. Integrate the vector field .dr, integrate the vector field .da. We have to describe the curve and the surface in a way that the integral will understand. In the case of line integrals, that means parameterizing the curve and then evaluating the function at all the points on that curve. And that's what this factor looks like. We take the vector field f and evaluate it at all the points on the curve. This is us describing all the points on the curve. And then we have to write dr in terms of t. We have to write the dr in terms of t. And so once we have the parameterization for describing all the points on the curve, we can calculate the velocity at all those points, and that stands in for the dr. So the dr says we're on the curve, and where is the curve headed next? And then this is where the curve is headed next, the r prime of t dt. So this matches the way we think about integration. We evaluate the function at a bunch of points, and then we add them up, or add up all those values. Area is equal to length times width, but the length is variable. So we assume that the length is constant for a little while so that we can use multiplication. But the big idea is that we're evaluating the function, the vector field in this case, at all the points on the curve. Switching down to flux integrals, we need to do the same thing. We're integrating this vector field f over the surface S. That means we need to evaluate the vector field f at all the points on the surface S. So here is one way that we described the surface. So in this case, we can describe S as the surface, where z is a function of x and y, and this is above the region R in the xy plane. This tells us what the surface looks like And above the region R in the XY plane is saying where to look. That's imagining, that compares to imagining the curve cruising around, and it's between t equals A and t equals B. That's telling us where to look, because the curve can go on forever. So just look at the curve between these two values of t. Just look at this surface above the region R. So this is where to look on the curve. And the region R is where to look on the surface. Where to look, I should say, values of t on the curve. That's okay. Above the region R, these are the values of x and y that we're going to plug in to this surface. So this is where to look on the surface. Just like when we're integrating a function, we find an antiderivative and plug in the endpoints. We have to decide the interval that we're looking at. Same thing here in flux integrals. Here we are describing the surface, and then the R is where to look on the surface. Any questions? All right. So next we should analyze what the dA represents. In the case of line integrals, dr just represents where things are headed. It's just the derivative at that point. With dA, we want that to be a vector where with an area, the dA is going to be an area, and the direction is going to be normal to, in this case, the surface. Well, it's normal to the surface S. Doesn't have to be, it's not in this case. It's normal to the surface S. So dA has a direction that's normal to the surface and an area that's going to be the magnitude of dA. Sorry, I stalled out there for a second. So dA, the vector, I don't want to use green. The vector dA is normal to the surface that's its direction, and its magnitude is the area, and the magnitude is the area. So the dA is going to be normal to the surface S, that's the direction, and it's going to have some area. Remember what we do when we're integrating. We assume that things are constant for a little while. We assume that f of x, going back to the beginning, we assume that f of x was constant for some small change delta x. This is so we get to use multiplication. We did the same thing in line integrals. Instead of having some curvy curve, we assume that the curve is a bunch of line segments, and then we just increase the resolution. We do the same thing with flux integrals. We're going to assume that the surface is a bunch of flat rectangular areas. And so we're going to need to measure the magnitude of the area. That's that's the amount that we're using, assuming that the vector field is constant. And we need to calculate a dot product. And so we're going to take the direction that's normal to the surface. So I need to calculate, I need a vector quantity that's going to be normal to the surface and whose area is going to be the magnitude. So I need to take a couple of vectors. The area is going to be a magnitude, and the direction is going to be normal. All right, so what must we be talking about? If we imagine a point on the surface, dang, I put this on the wrong side. If we imagine a point on the surface, and let's look at this from the top down. What we're going to do, so the point on the surface here is going to be at, there's going to be some x coordinate in the I direction, some y coordinate in the j direction, and the z coordinate will be f at x, y in the k direction. I'm going to want to know what direction things are going in. I don't know if this is a too much coffee problem or a not enough coffee problem, but I attribute all my problems in the morning to the correct quantity of coffee. It usually comes down to, do I have the correct quantity of coffee? But the caffeine addict in me says the answer is always get more coffee. That's the correct amount of coffee. So, should have paused the video so I could kind of reset, but I decided to press on. Probably a bad idea. That's fine. Really, I was just waiting to ask the question. I want a vector that's normal to the surface, and I want the magnitude of that vector to be the area. How am I going to combine two vectors so that I get something that's normal to the surface and whose magnitude is area? How do I combine two vectors and get a vector normal to those two vectors? Anybody see what's coming up? Because what we really need to do, yesterday I waved my hands at the minus fx minus fy plus k so that we could do a calculation. So I was like, I'll wave my hands. Sure, they're negative because they need to be. But today I don't want to wave my hands. I want to convince you. Even though I'm fairly convinced that y'all are convinced if I just said, that's just how it works. But that should never be good enough. It should never be, seems reasonable should never be good enough. You should always press anybody that's like, oh, doesn't that seem reasonable? So we're going to imagine on this surface, here's the point on the surface, x, y, and f at x, y. Those are the points x, y, and there's the z coordinate. So we need to create, we're going to take a tangent plane to the surface. We're going to imagine a little piece of a tangent plane to the surface. So there's going to be a vector in the x direction, and there's going to be a vector in the y direction. And these are going to be, there's going to be a vector in the x direction and a vector in the y direction. Let's give this a name. So in the x direction, we're going to need the derivative in that direction with respect to x. So it's going to give us a 1i plus 0j, and then the derivative of f with respect to x. Following a similar thing, similarly, the derivative in the y direction will be ry. So the derivative with respect to y is going to be 0i plus 1j plus fy times k. So looking top down, here's the rx and then the ry of that tangent plane. For the derivative in the x direction, for the vector in the y direction, I need to combine these two vectors so that the magnitude ends up being an area and the direction is normal. So here is how we're going to construct our dA. I'm combining two vectors and I want a vector. What's the only thing that we can do? Since I'm trying to combine two vectors and end up with a vector, I must be doing a cross product. I'm going to combine Rx and Ry into a vector that's perpendicular to Rx and Ry. That all says cross product. And so that's what we're going to do. We want the cross product of Rx and Ry. Oops, I spelled cross product wrong. Yikes. It makes sense that we're going to use a cross product because the cross product is perpendicular to the two vectors, and the magnitude of the cross product is the area of the parallelogram. So this fits with everything we know about the cross product. Magnitude of cross product is area. And the cross product is perpendicular to both vectors. Those are the things that we're going for. Normal and magnitude is area. Product is area, cross product is area, cross product is normal. dA is a parallelogram. So we just make the tangent plane. Here's a point on the surface. We make a tangent plane at that point, and then find the cross product of the Rx and the Ry. Any questions? So this is going to be the determinant. So I, 1 and 0, J, 0, and then 1, and K, Fx and Fy. So now we can see that the Fx and Fy are going to show up negative. Any questions? Comments? Deep thoughts? All right, let's pause the video here and talk about what's coming next.